Simple example to address the cache line placement policy, cache line replacement policy, and cache line identification policy. So for cache line placement policy, there are two methods are there, but we are going to follow three methods in our course. One is cache direct mapped cache method, then fully associative cache method, okay, and set associative cache method. So to address this, what is direct mapped cache method means? For each block of memory, there is a specific cache line is assigned in the cache memory. That is, if the cache line is in the cache, only one specific slot for it based on its tag, which is computed based on memory address of the block. And let us see how it makes the solution for all these three questions like cache line placement, cache line identification, and replacement policies. As mentioned, cache line placement means it goes to its one assigned slot based on its tag, and cache line identification is it look at the tag for one assigned one by following the cache line matching algorithm, that is incoming tag is equal to the stored tag. Then the cache replacement policy, that which cache line, existing cache line should be kicked out to assign the same spot for the another cache line. Then in the writing strategy, it allocates on the write but more on write strategy. We will discuss more on it later. So let's have this with the example to understand those. Assume that we have a cache line having we have cache memory having 4 cache lines. So in the frame valid field, initially the cache memory is empty, so the valid bits are set to 0. And there are no cache line addresses inside the cache memory because no block of data is available inside the cache memory. So there are 4 locations in our cache, and assume that each block size is 1 byte, which is going to store in the data field. And then let's assume that program counter or the CPU requests the references to the memory addresses or memory stream like 0, 1, 2, 3, 4, 5, then 2, 3, 7, like that. So total 9 requests. So these requests are executed sequentially in a linear manner in the pipeline. So then what is the first step in direct mapped caching? Computing the cache line address, that is tag address. So that, when we talk about the cache line address, we will have the complete details about this tag part, because for the program counter address size, if you treat 32-bit, the higher order few bits are used for cache line address purpose, that is tag address. We will talk more about this later. So then how to mapping the block of memory to these slots. So in direct mapped caching, it follows the modular operation for slot allotments. That is, the slot is computed as the block address, that block memory address, doing modular operation with the size of the cache. So in our example, it is the size of the cache is 4. There are 4 cache lines. So for the 0th block, which slot is assigned in the cache memory means the block address over the modular size, that is 0 modular 4 is equal to 0, that 0th slot is assigned. So in the execution time, when program counter request tag 0, that means in 0th slot, it is going to compare the stored tag. Tag 0 means in 0 slot, this tag is going to be compared. So here, if the incoming tag is not equal to the stored tag, that means there is a cache miss. So in the cache this gives the cache identification policy from direct mapped caching. Second, when there is a cache miss, the block memory, the block from the memory address 0, that should be fetched and hold a copy in the cache memory at slot 0. So that is cache placement policy. So where for this block 0, which slot is assigned means slot 0 is assigned. So fetching the block from the main memory, that is the block address at 0. So it is having the data. Okay. So in which slot? For this block, slot 0 is assigned. So it is copied and set the valid bit 1. And the cache line address, which will be computed from this block address, that is the higher order bits are used to identify the cache line. That is tag. That is identified like for block 0, it is cache line 0. That is the tag value is 0. So the same thing applied for the next sequence of memory access, that is 1, 2, 3, 4, 5, then again 2, then again 3, and then again 7. So which slots are assignment? For block 1, the slot 1 is assigned. So when CPU trying to access this block, the piece of data from block 1, then it first search in the cache memory. So which slot is assigned means slot 1. So in slot 1, the tag is going to be compared. So in slot 1, there is no stored tags. So then there is a cache miss. Then cache placement policy exists. So this block 1 is fetching from the main memory and a copy is loaded into slot 1 and set the valid bit 1 and the tag address is 1. But the next block, block 2, which slot is assigned means 2 modular 4 is equal to 2. Second slot is assigned for block 2. Then for cache identification, incoming tag compared with slot 2 tag, there is a cache miss. Then cache placement policy will take place. Fetch block 2 and load a copy in the data field of slot 2 and set the valid bit 1 and update the tag field of the frame with the cache line address that is 2. Then for third block, slot 3 is assigned. That will be for cache line identification. It goes to third slot, compare the tag, there is a cache miss. Then this continues similar to the previous 3 operations. So up to now, the direct map method addressed that cache line identification policy, second, cache line placement policy. So now it is interesting that the cache memory is full. So the next sequence here is trying to access block 4. So which slot is assigning for block 4 means the 4th block, 4 modular 4 is equal to 0. So 0th slot is assigned. But in the cache memory, this slot is already occupied with some other cache lines. So how to identify that? Because in the valid field, the data is 1. That means the requested data might be there. But how to identify whether this data is valid or invalid? So that is, again, going through the cache identification policy. So tag 4. So which one? For the fourth block, slot 0 is assigned. So that tag is compared with the stored tag. It is 0. So 4 is not equal to 0. Okay. So that means there is a cache miss. So then in cache replacement policy, first of all, the cache line 0 should be evicted, the existing data. Then there is a cache miss. So C is the yellow field here. It is evicted, the data is evicted. Then the data from block 4 from memory will be fetched and load a copy into slot 0 cache line and then set the valid bit and update the tag address. So the next, it is accessing 5. So for the fifth block, which slot is assigned? Means 5 modular 4 is 1. Slot 1 is assigned. So for this, in slot 1, tag 5 is going to compare. That is, incoming tag is compared with the stored tag. It's not matching. That means the existing data is a dirty data. So then first it must, because there is a cache miss, so it must be evicted. And then block 5 data is fetched and load into slot 1. Set the valid bit 1, update the tag address of the cache line, that is 5. So this is addressing the cache replacement and placement policy. Next sequence is, again, it is requesting the block 2, the piece of data in the block 2. So which slot for this block 2 means? Second slot is assigned. So in the second slot, if the incoming tag compared with the second slot tag is matching, so then there is a cache hit. The next, requesting block piece of data from block 3. Which slot assigned for block 3 in the cache memory? It is third slot. Then the incoming tag compared with the stored tag. So there is a incoming tag matching with stored tag. So again, there is a cache hit. Right? So then here, if you observe that when the cache is full, then for some requested tags, there is a cache miss. For some requested tag, there is a cache hit. That is, it addresses the program locality. The next sequence is the 7 then. So the block 7, which slot is for the 7th block? It's 7 modular 4, slot 3 is assigned. When trying to access piece of data from this block, the incoming tag is not equal to stored tag. So then there is a cache miss. When there is a cache miss, cache replacement. So that is evict that block of data from that cache line 3 and then place the block of data in cache line 3 or slot 3 and set the value, update it and update the tag address. So if you compute the performance of this cache based on the direct map caching for accessing the data, for the references, the stream of references from 0 to this, total 9. Right? So there are 9 access in total. Out of 9, to find the hit rate, out of 9 times, there are 2 hits here. So that gives the hit rate. So that is almost equal to 22.9%. And if you compute the miss rate, so out of 9 times, 7 times the data is miss. So that's equal to, what is the miss rate means? It is almost 77.8%. 77.8%. So that is the miss rate. Then what is the overall memory access stage then? How to compute that? Because in this process, when there is a miss, main memory is accessed. When there is a hit, cache memory is accessed. So it is a combination of main memory access and cache memory access. So then what is the average memory access time? So that average memory access time, to compute that one, let me quickly show you the performance equation here. The average memory access time for hit and miss is computed as the hit latency. When there is a hit, it is accessing from the cache, so it takes let latency. And hit rate plus miss latency plus miss rate. So miss rate means it is miss penalty because the copy is not available. The copy is not available in the cache memory. So then it's required additional time to access main memory. So this miss rate means the miss penalty. Typically, the miss latency means the latency hit plus miss penalty. The miss penalty is, we just discussed in the access time plus transfer time. So for this example, suppose in our example, out of 9 times, the 2 hits were there and 7 miss were there. So hit rate plus miss rate, by assuming that the hit latency is 1 nanosecond and for miss accessing from the main memory takes 100 nanoseconds, and by substituting these values in this equation, it gives the 78.9 nanoseconds. So that is the average memory access time. It is the average memory access time. So that means out of 100 nanoseconds, by keeping a cache memory in between main memory and CPU and following the direct mapped cache method, that reduced an average 21.8 nanoseconds of execution time. So the performance, the execution time, the response time is reduced. So the performance is increased.